Right, so for today, we're gonna solve indeterminate members. So let's have an introduction first, as usual. If the equilibrium equations are sufficient to calculate all the forces, including support reactions that act on a body, these forces are said to be statically determinate. So far, that is what we've been solving, meaning the number of reactions and forces is equal to the number of equations that we can make from your equilibrium analysis or equilibrium equations. Now we're going to start discussing statically indeterminate members or statically indeterminate problems. So here, if the number of unknown forces exceeds the number of independent equilibrium equations, you have a statically indeterminate member. So since we're missing equations, we're going to use compatibility equations. So these are mathematical expressions of the geometrical restrictions imposed on deformation. So previously, we've been using equilibrium equations to solve, right? Now we're going to add compatibility equations. So they give an additional equation in order to complete our solution, right? So these are the steps. First, as usual, draw the FBD and derive equations of equilibrium, same as what we've been doing so far. Next, draw a sketch that exaggerates the magnitude of deformations and derive the compatibility equations. Now, usually these are just, or compatibility equations are just observations of your deformation. So later on, you'll see what that means. And then next, use Hooke's law to express deformations or strains in the compatibility equation in terms of forces or stresses. Or you can also express your stresses or forces in your equilibrium equations in terms of the other. So remember, stress is just force over area. So force is just stress times area. So you can use that to convert or to express one in terms of the other. Force in terms of stress or stress in terms of force. And then lastly, just solve. Alright, it's pretty straightforward. That's it for the intro. Now we can start with the examples. Alright, let's start with number one. Number one, the concrete post in the figure is reinforced axially with four symmetrically placed steel bars, each of cross-sectional area 900 millimeters squared. Compute the stress in each material when the 1000 kilonewton axial load is applied. The moduli of elasticity are 200 GPa for steel and 14 GPa for concrete. So let's write out the given for that. But first, let me just copy that figure. Okay. Copy. Okay, again, first, let's write the given. So you have this drawing. Cross-sectional area 900 millimeters squared. So write it there. What else? And of course, 1000. And E is 200 for steel and 14 for concrete. So E for steel, let's call that ST. 200. And then for concrete, let's call that C14. Okay, so first thing here is draw your free body diagram. Let me just silent that. Alright, so draw your FBD. So this is pretty simple. So you have this bearing plate here. You have this force. which is 1,000 kilonewtons. And then this 1,000 kilonewtons will be carried by your steel and your concrete. So your steel and concrete will react. So let's draw this. Okay. So at these ends, we have reactions at steel. Okay. So let's call that ST. And not only that, your concrete will also react. Let's say this way. So let's call force reaction of concrete as TC. Okay? Gitna ko lang to. After that, knowing that these are your reactions, you can start writing out your equilibrium equation. So here, summation of forces, Y, since they're all vertical, or V equals 0. So you get the number of reactions for your steel would be 4 because there's 4 steel members or steel bars. So all of these steel bars will counter this force. So it's 4. So 4 reactions for your steel bar. Then your concrete will act as 1, which is plus the reaction of concrete. Then since they're all upward positive, then 1,000 kilonewton downward, therefore negative. So minus 100,000. And this is kilonewton. Usually we're working with Newton and millimeters, convert this to Newton. And then look here at our first problem. We're looking for stress. Compute the stress in each material. So depending on what you're looking for, you're gonna express your terms in to the term that we're looking for. So here we have forces, express that in terms of stress. And again, stress is just force over area. Therefore, force is just stress n times area. Okay? So convert all of these to stresses. So 4 and stress of steel times area, cross-sectional area of steel, plus stress of concrete times cross-sectional area of concrete, then equals, transpose this to the other side. I'll just write this in scientific notation, okay? So 1 times 10 raised to 6. So now you have your equation number 1. And as you can see, we have two unknowns, stress in steel and stress in concrete. We only have one equation. So the other equation will come from your deformation. Okay, so let's imagine this. Right, you have this force here. It's gonna compress this system. So let's say this is your original system, right? Then you have your bars over here. And then this, your force will compress this. So the final position now will be somewhere here. This is now the final position. So now your bars, let's give them some color. And then let's go. Okay. So your bars deformed by this length, right? Initial position, this is now your final position. Again, initial. Yeah. Okay. Ayan. So again, starting point and point. So your bars reduced by this amount. So that is your deformation for your steel bar. And then notice, okay, your concrete also deformed by that much. Okay, you can see here. Okay. So that's your deformation of concrete. Now, based on this drawing, you can say that deformation of concrete is equal to deformation of steel, right? So you can create an equation out of that. Deformation of concrete equals deformation of steel. Okay? And then remember the equation for steel, deformation, it's PL over AE. Again, we're looking for stress. P over A is stress, so we can just write sigma L over E. Okay? So sigma L over E of concrete. Again, this just means all of concrete. Then sigma L over E for steel. Now just sub in your values. So sigma ST, sigma C. Then this is length of concrete, original length of concrete, and original length of steel member. And as you can see, they're equal, right? Based on this drawing. Therefore, I can just cancel out L. So I'm left with stress of concrete over modulus of elasticity of concrete, which is given 14 GPa. And our units are in MPa or newtons per millimeter squared, so convert GPa to MPa, and that's just times 1,000. So 14 times 1,000 or times 10 raised to 3 equals stress of steel over, again, GPa to MPa times 10 raised to 3. Multiply both sides by 14 and 200, you're gonna get, ready your calculators, 200 times 10 raised to 3 sigma C equals this, then transpose to the left, we're gonna get minus 14 times 10 raised to 3 sigma ST equals 0. And now you have your second equation there. You have two equations, two unknowns. You can now solve for stresses in steel and concrete. Steel, stress in concrete. Okay, please solve. If you remember the shortcut for solving simultaneous equations, right? You're gonna use the equation of your calculator. So for me, it's just mode 5 equation. Mode 5. EQN. You're gonna choose AX plus BY equals CN. Then A would be 4 times A, which is 900. B would be AC, and so on and so forth. Actually, let me write that. Sigma ST times 4 times area of your steel member is this cross-sectional area. Okay, it's a circle, therefore times pi over 4 wait, I think it's given. Steel bars, cross-sectional area 900. Okay, it's already given. So this is for steel bars. So times 900 ASP plus area of your concrete. So this is your concrete. Then you're just gonna subtract the area of your steel members. So times, this is 300 by 300. So 300 squared minus 4 times 900. Ano, solve nyo na? No. Okay, correct, John. Stress in steel is 103.65, correct, and then in concrete 7.25 or 26. Okay, very good. 103.65, and remember units are in newtons and millimeters, so this is MPa. Then for concrete 7.26 MPa. So better practice solving simultaneous equations because there's gonna be a lot of those for indeterminate members. Okay. Any questions for that? Number one? Wala. Okay. None. Okay, do you understand number one? Please answer yes or no. Okay, good. Next, let's answer next one. Number two. Okay. Number two. A steel bar 50 millimeters in diameter and 2 meters long is surrounded by a shell of a cast iron 5 millimeters thick. Compute the load that will compress the combined bar, a total of 0.8 millimeters in the length of 2 meters. For steel, E is 200, and for cast iron, E is 100 GPa. So we're looking for the load that will compress your steel by that amount, by the given amount. Again, let me copy this. Paste it here. Paste. Okay, again, let's write out our given. It's not given. 50 millimeter diameter. Ito siya. Your bar. Then cast iron, 5 millimeters thick, and given. then your total compression is equal to 0.8 millimeters, and that's just deformation. 0.8 millimeters in the length of 2 meters. So that just means, yeah, this is your 2 meter length or 200 millimeter length or 2000 millimeter length. Yeah, it's gonna compress along this length. That's all that means. Then E 200 and 100. So again, E of steel, 200, then cast iron, or just I na lang. Iron, 100. Okay, so we're looking for force that will deform this. Again, one of the first things we'll do is create your free body diagram. How will our reactions act? So first you have your force P. So there's no horizontal member here, so just draw a point. Then your external force P, downward. And then your steel bar and your cast iron plating will react. So let's start with your steel bar. Okay. It's gonna react upward, counter this force. And along that same line, the axis of your member, right? Hindi pa lang kita. Yan, okay. Again, reaction of your steel bar. And then reaction of your iron bar. So basically, your summation of forces y equals 0, that's just negative P plus PST plus PI equals 0, or PST plus PI equals P. Okay, and then we're looking for P. So this is now your equation 1. Next, actually this is 3 unknowns. So now I need to create another equation based again on your deformation. So drawing cross section of this. Right? Let's say this is your iron. Then this is your steel, and then this is your iron plating. Okay. So because of this force, again, all of this will compress, okay, to this total length, or to this final length. Okay. Okay. So now you have a deformation of your iron plate, your steel bar. Okay, it's gonna deform by this much. So that's a deformation of your steel bar. And then at the same time, your iron bar is deforming as well. Okay. So that's also the deformation of your iron bar. So based on this drawing, once again, deformation of steel equals deformation of iron. And we have a condition here. It's going to compress by a length of 0.8 millimeters. So this is equal to 0.8 millimeters. Okay, so that's your equation. Now, just sub in your values. We're looking for P. So use the equation for deformation as PL over AE. So PL over AE of steel equals PL over AE of your iron, also equal to 0.8. Okay. So next, P. This is P of steel. Length of steel is given 2000 millimeters. Area of steel is also given, or you can compute for it. This is your steel cross section. So it's a circle. So just pi over 4d squared, and the diameter of your steel is 50. So pi over 4, 50 squared. Pi over 4d squared, then E of steel is 200. So 200, again, convert to MPa, so times 1000, or times 10 raised to 3. And this is also equal to Pi. For iron, length of iron is the same. It's also 2000 millimeters over area of your iron. So it's just this ring, right? So to get the area of that ring, it's just outer diameter minus inner diameter. So pi over 4, outer diameter 60 squared minus inner diameter 50 squared. Okay? Then times E, which is 100. Again, all of this is equal to 0.8. Now what? Well, I can equate this to this, then I can solve for PST. Then I can equate this to this, and I can solve for PI, right? So please solve what's PST and what's PI. Okay, correct. Miguel, it's 34557.52. And that is for your iron, right? Or you can just rewrite that as 11,000 pi, so that you don't have to store this value. And 11,000 pi. So is that Cantara. And then ST. Correct, Lawrence, 15,000, 157,000. Or again, you can just write that is 50,000 pi. I think the reason why I'm writing it this way so that I don't have to store these values. Correct, Lawrence. Okay. Now, I have P, I have PST. Again, our goal is to solve for P. So using equation 1, P equals PST plus PI. PST is 50,000 pi plus 11,000 pi. So final answer. Right, 61,000 pi. But for final answer, you're gonna have to write the decimal form, so 191,637.50 newtons. Correct, John? And Erica? So Bruce Gutierrez. Okay. That's number 2. Any questions for number 2? None? Okay. Do you understand number 2? Please answer yes or no. Okay, good. Let's move on to number 3. Okay. The rigid platform in the figure has negligible mass and rests on 2 steel bars, each 250 millimeters long. The center bar is aluminum and 249.90 millimeters long. Compute the stress in the aluminum bar after the center load 400 kilonewton has been applied. For each steel bar, the area is 1,200 millimeters squared and E is 200 GPa. For the aluminum bar, area is 2,400 millimeters squared and E is 70 GPa. We're looking for stress again. And specifically stress of your aluminum bar. Okay, so again, facing the alright. So first step, once again, write your given. So length of your steel bar 250 mm. So length of steel 250 mm. What else? Center bar 249.90. So AL. What else? Load is 400 kilonewton. Yeah, 400 kilonewton. Then area of steel bar 1,200 and 200. Then area of aluminum bar 2,400. This is for steel. Okay, so that's all you're given. So again, first write out your equilibrium equations and draw your FPD. Okay. So obviously your steel is gonna react to this force and it's applied at these points. So that's your reaction of steel. Let's call that PST. Okay. Next, if you move this, so you're gonna assume, is this 400 kilonewton force enough to touch this aluminum bar or to close that gap? Okay, you're gonna assume first. So let's say yes, it is. Therefore, this aluminum bar will react as well. Will counter that force. Okay, so you're gonna have this reaction, your PAL. Okay. So again, we're working under the assumption that 400 kilonewtons is enough to close this gap. Okay, and the next summation of forces equals 0. Okay, you have PST plus PST, so that's 2 PST upward, therefore positive, plus PAL upward, therefore positive, and then minus P, or minus 400 kilonewton equals 0. Okay? We're looking for stress, so I need to rewrite these forces in terms of stress, and that's just stress times area. So twice stress of steel times area of steel plus stress of aluminum, area of aluminum. Then transpose this to the right, 400 times 10 raised to 3. And then I'm going to input our given. So this 2 times area of ST is 1,200. ST plus area of your aluminum 2,400. Okay. And again, you have your equation number 1. Two equations, only two unknowns, one equation. So again, I need to create an equation out of the deformation. Okay. So let's get this. Okay. Okay. I don't know if you can see it. So it's already dimensions first. Okay. So focus here at the drawing. So this is your original figure, right? And then this. Again, this is your original. Then after applying this force, then everything is compressed to this final position, alright? So what happens, okay, first of all, this is the original position of your steel bar, right? Then this is the final position after being compressed. So therefore, this length is your deformation of steel bar. Now, not only that, this force was enough. Again, our assumption is this force is enough to close the gap. But not only that, it's also enough to compress your aluminum bar. So after moving downward, it's going to move further and compress your aluminum bar. So this is the original position of your aluminum bar, and this is the final. Okay. So it compressed by this amount. So that's your deformation of aluminum bar. And then, okay, this gap, since this length is 250, right, your steel member, this length is 249.90, the difference between those two is the length of your gap or height of your gap. So 250 minus 249.90, that's just 0.1 millimeters. So this gap right here is 0.1. Now looking at the drawing, I can create an equation. What? As you can see, this total length, right, and that total deformation, your delta ST deformation of steel, is actually equal to 0.1 plus the deformation of aluminum, okay, according to this drawing. As you can see, this is 0.1 and this is deformation of aluminum. Okay, now I can create that equation. Right? So deformation of steel again equals deformation of aluminum plus 0.1. Again, we're looking for stress. So deformation of steel is sigma L over E. So sigma L over E. Again, this is of steel equals sigma L over E of aluminum plus 0.1. Then plug in your values. So this sigma ST, original length of your steel is given 250 all over E. E of steel is 200. So 200 times 10 raised to 3 equals sigma of aluminum, stress of aluminum times original length of aluminum bar to 49.90. All over E of aluminum 70 plus 0.1. Okay, and that is your equation number 2. Two equations, two unknowns. I can now solve for stress in your aluminum bar. Okay, please solve. Equation 1, equation 2. But we're only looking for aluminum. So using that, you can solve for aluminum. Correct again, John. Aluminum is 22.48 MPa. Nakuha nyo ba to? Try nyo recompute hanggang sa makuha nyo 22.48. Again, try to practice solving for simultaneous equations. Okay. All right. Any questions for number 3? If you don't have any questions, do you understand number 3 then? If you do, please answer yes or no. Okay, good. So now, kayo naman pag-iisipin ko ng deformation equations para ma-practice. Okay. Let's start with number 4. Homogeneous bar with a cross-sectional area of 500 millimeters squared is attached to rigid supports. It carries the actual loads 25 kilonewton and 50 kilonewton applied as shown in the figure. Determine the stress in segment BC. So we're looking for stress in segment BC. Now usually this would have been easy to solve if it's only restrained on one end, right? You already know how to solve for problems like that. However, this is restrained on two ends, so it's not able to deform freely or move freely. Okay, so what we're gonna do here is first write out our given. So P125, P250. What else? Area is 500. Yun lang. So we're looking for stress in segment BC. Okay, wait lang. Right back. So one of the first things to do is, as usual, draw your FBD. So you have this, you have this. Draw your reactions. So these are intelligent guesses again. So let's say, since my forces are to the right, perhaps my reactions are to the left. So let's call this RD. And then my reaction at A is also to the left, RA. So from this, I can create an equation. Okay. Let's write it here. Summation of forces X equals 0. So negative RA plus 25 plus 50 kilonewtons minus RD equals 0. Transpose, I get RA plus RD equals 25 plus 50, that's 75 kilonewtons. So 75,000. Okay, now I have an equation. That's your equation number 1. What else? I have 2 unknowns here, so that's not enough. So another thing that we can do now is, our goal here is to find out the stress in member BC. Okay. So we can isolate that. Since usually that is what we do, right? So we can do that as well. So this is your point B. You have an external force here of 25. And then you have your reaction, RA. Now we're going to make an intelligent guess again. San, where do you think the direction of your internal force between B and C would be? Okay, so this is your PBC. Now, if this is 25 to the right, I have a reaction to the left. Right? So my guess, again, this is just an intelligent guess. My guess is RA is greater than 25. So therefore, to balance this out, the direction of my BC should be to the right. So again, this is just a guess. I'll show you later what happens if you make an incorrect guess. So from this, I can create another equation. Again, summation of forces X equals 0. Negative RA plus 25 plus PBC equals 0. Remember, I know area. If I am able to figure out what this internal force PBC is, I can solve for its stress. Because stress is just force over area. So my goal now is to solve for this. Right, so PBC now equal to RA minus 25. So we have another equation. Call that your equation number 2. But as you can see, now we have 3 unknowns. So I need another equation which we'll get from our compatibility equation. Okay. So now what will happen? I have these forces right here. Okay. Let's try to draw that. Okay. So what you need to know now is, how will these bars or your segment move? Okay. So that depends on its internal force. So let's start with section AB. Okay. So AB, if you cut this out, there's a reaction here. right? So drawing the dito, right? So your AB, so you have a reaction here. We've already drawn it to the left. Therefore, internal force in AB will be to the right. And it will be tension because it's away from your force. Therefore, if it's a tension force, your AB will elongate, right? It's gonna elongate. So let's say this is the final position now of your AB. Let's call that B prime. Now do the same for BC and CD. BC, I've already done that. It's this direction away from the member. So C is also gonna elongate, or BC is also gonna elongate. Okay? There. And then do the same for the last segment CD. CD, okay, let's draw that. Okay. Oops. Okay. You have a reaction here, RD to the left. Therefore, the internal force between C and D would be to the right. And it's towards your member. Therefore, it's in compression. Therefore, your member CD will actually compress. Okay, okay, right. So AB and BC are in compression, while AB and BC are gonna elongate, while segment CD is in compression. Knowing that fact, or knowing that premise, how am I gonna write my deformation? So AB, BC, CD. What is the relationship between those three? Can somebody give me an equation relating those three, knowing that A, B, and BC are elongating while CD is compressing, and they're not allowed to move? Since you have constraints on both sides, so total length will remain the same. What can you say about their elongation and compression if it's restricted? Isipin nyo. Dalawa nag-elongate, isa nagko-compress. What is the equation? What can you say about the magnitude of their deformations? Bigyan ko kayong clue. Let's do a simpler analysis. Yeah. You have two segments na lang, and they're both restricted. Okay. So let's say section AB is elongating, right? Therefore, section BC should compress. So, okay, since they're not gonna move, since this is elongating your section AB, the length of your BC will shorten. And again, since it's the same length, okay, it's restricted, it's gonna deform by the same amount. Okay. Therefore, I can say elongation of AB, the magnitude of the elongation of AB is equal to the magnitude of the compression of BC. Since again, they end up at the same length since it's restricted. So the amount it elongates should also equal the amount it compresses for it to remain the same length. So now that I have three segments, how will I get my equation? How should I write my equation? Okay, very good, Miguel. It's AB plus BC equals CD. Correct. Why? Again, the amount, if your bar is restricted on both ends, the amount it elongates should equal the amount it compresses, okay, for it to remain the same length. So AB and BC are in elongation, so AB plus BC would equal the compression of your last segment CD. Okay, so now this is my working equation. Okay, very good, Miguel. So now I can use this. Let's just move it upwards. What are we looking for again? Stress. But I need to know first PBC. So I'm going to use PL over AE, even though I'm looking for stress. So PL over AE. So this would be stress in AB, PL over AB, AE of AB plus PL over AE of section BC equals PL over AE of section CD. Now let's see here. They all have uniform area, so I can cancel out area, and they're all made of the same material, right? Yeah? It's not specified homogeneous bar, therefore they're all the same material, therefore they have the same E. So I can cancel out AE, AE, or multiply everything by AE, AE cancels out. Okay. So I'm left with PAB, okay, times L, and original length of that is 0.60, plus PBC times LBC, which is 1.20 meters, convert to millimeters, sorry. 0.6 meters times 1,600. So 600 millimeters. Plus PBC times this, 1,200 millimeters. Equals PCD times this, 900. Now look here. Lalong dumami unknown ko. I don't know PAD, PCD, but if you remember what we did earlier, okay, let's redraw. Quick drawing. So you have RA over here. Therefore, the reaction here would be, so PAB. Do the same thing for the last one. And there's a reaction here, RD. Therefore, PAB reaction would be this way. Our internal force would be this way. That's your PCD. Okay. And using equilibrium equation, summation of forces X here. PAB equals RA. Do the same thing here. Okay. PCD equals RD. So just sub in these values here. PAB is RA, so RA times 600, or just 600 RA plus 1,200 PBC. And PBC is just RA minus 25. So I'm going to solve for RA first, then I can solve for PBC. So RA minus 25 equals 900 PCDRD. Okay, two equations, two unknowns. RA and RD here, RA and RD as well. I can solve for RA and RD. But I only need RA to solve for PBC. So what's RA? Mga wala pang recitation dyan, sagot na. Solve for RA. So, ayan. Or if you want, you can write RD equals 75,000 minus RA, sub that here to solve for RA. Or again, you can just use simultaneous equations for your calculator. And yung first number. Anong sagot? No, it's not 37,000. Oh, correct, Lawrence. 36.11, that's in kilonewtons. Right. Oh, okay, my bad. So this is in newtons. This is in kilonewtons. 25,000. 25,000. Anyway, wait lang. Again, correct, Lawrence. 36.11 kilonewtons or wait. Okay. 36.11 or this is all in newtons na ako. 36,111.11 newton. Now, sub in equation 2. Sub in 2. I can finally solve for PBC. So what's PBC? 1, 1, 1, 1, 1. Limang 1. Nakakuha. Correct, John. 1, 2, 3. Correct, Dian. 2, 3, 4, 5. And Erica. John, Dian, Erica. Okay. 1, 2, 3, 4, 5. And if you've noticed, all of these are positive. Therefore, all my assumptions for directions are correct. Therefore, this is the correct direction for PBC, and therefore, this is in tension. So finally, to get for stress, solve for stress in PBC, in BC, that's just PBC over A. PBC is 11,111.11 divided by 500. What's the final answer? Correct, Lawrence, it's 22.22. And in tension, this is tensile stress. Okay. There. So that is what happens when you have a correct assumption. Okay? So what if you have an incorrect assumption? What's gonna happen? So we're gonna solve it this way now. Okay. Let me show it to you first. So for an incorrect assumption, let's say I assumed this is to the left, right? Okay. Therefore, this equation will change. It's now negative. Therefore, now this becomes negative RE plus 25,000. Not only that, my drawing will change as well. Since this is compression, okay, so all your succeeding equations should be constant with your, or uniform with your assumption. If I assume this is to the left, therefore compression, therefore member BC would compress as well, or it should compress. Okay, therefore that's your C prime. Therefore, this equation will change. It's now the elongation of AB is equal to the compression of BC and CD. Okay, ganyan na siya. So equals plus equals plus equals plus. You're still gonna get RA is 36,111.11. But if you sub it here, okay, you're gonna get negative. Okay? So that negative just means you have an incorrect assumption. So you're gonna just flip your direction around. So therefore, PBC is to the right and it should be in tension. Okay? So that's all you need to do. So that's the only thing that happens when you have an incorrect assumption. Your directions change, your sign will be negative for the final answer. But make sure your succeeding equations are in line with your previous assumptions. So for example here, since this is now compression, my compatibility equation changes as well. And this will be your answer or your solution. Okay? So you can try this out, solving with an incorrect assumption, or this is solving with a correct assumption. Alright? Do you understand? Any questions? None. If you understand, please answer yes or no. Okay, great. Again, correct assumption, incorrect assumption. Right, wala nang tanong? Wala na. Okay. It's almost time, so I'm gonna continue this next meeting. So indeterminate members next meeting, and then on Saturday you're gonna have your seat work number 2, right? And then next week, submission of your project, your reviewer. It's the submission link is already there, so you can submit as early as now. And you're gonna have a group activity on Saturday as next week as well, since that's your 4th week, right? Week 8. So review for your group activity, same groupings. By the way, for those who don't have group mates yet, next meeting, okay? Let me know, remind me next meeting because we're gonna have a lot of free time since there's only 2 questions left. So again, for those who don't have group mates yet, remind me next meeting. I'm gonna join you in a group, okay, for the group activity next week. And obviously next week as well is your modular exam number 2. And then if you've noticed, if you looked at your syllabus, I still need to discuss thermal deformation. So I'm just gonna move that to module number 3. Okay? So yun lang. So this will be the last topic for this module, I believe. Indeterminate members. Or if not, I'll let you know if I change my mind. Okay. So any questions? Please answer yes or no. Any questions? Okay, great. Since you don't have any questions, you may go. Goodbye, class.